qubit degree of freedom with this GE alternate states. And the Hamiltonian would be modified, but not actually in such a complicated way if you look at it carefully. So the Hamiltonian looks precisely the same, but here we project onto the ground, so the lowest electronic state. So the Hamiltonian only applies to the states that we said it applied to up here. And we have this extra term which just accounts for the extra energy. But actually, we'll see shortly that this is a feature of the system that we can use and take to our advantage rather than a bug, rather than a problem. So we'll actually need this. OK, so before I mentioned that if you're able to engineer a Hamiltonian with SN cross SUD symmetry, then you could infer the spectrum using that system, provided you could satisfy these characteristics. The system that we just described is this one, represented by this one here. And it is indeed a Hamiltonian with SN cross SUD symmetry, and it should be experimentally realizable, and it should be possible to prepare the initial state that we desire, so that's good. However, there's no reasonable way to measure the energy in this system. And also, it turns out that you can solve the Hamiltonian I wrote down, and it is not invertible. So there are multiple irreps with the same energy. However, good news is, and what we've been able to show is that if you include this extra electronic degree of freedom, and you can take it to your advantage, you can take advantage of it, then you need to be able to do the following thing. So again, prepare the same state, all the atoms in a row and all in the lowest electronic state. You should also be able to apply some unitary pulse, some unitary transformation, which transforms between these two different states on the atoms. And you should also be able to measure the number of atoms which are in E versus G. And if you can do that, then you can infer P, and I'll describe in a second how that would work. But the key thing is these should all be possible experimentally. So that's the Hamiltonian that we had. And I just want to describe now what the experimentalist should do in order to implement this. So the experimentalist should build the trap, the square trap. They should prepare the state of the atoms, the nuclear spin state of the atoms, all in the lowest electronic state, but the state of the nuclear spin should be rho. Then they should apply a pulse, this V beta, which is a partial transformation, a partial rotation between the lowest and the first excited electronic state of strength beta. Then they should just leave the Hamiltonian to evolve the system for a little while, for some time t. Then they should invert the pulse that they applied before. And when they do that, it's worth pointing out that, we applied a pulse and then we inverted it, and in between we allowed the Hamiltonian to evolve the system. If we hadn't allowed the Hamiltonian to evolve the system, we would have done nothing. But the Hamiltonian has evolved the system, and because of that, we don't get the original state that we started with back. There's some atoms which are left in the excited state E after this process. So that's really our signal that we would measure, is how many atoms are still left in E. And that's what picks up some information from the Hamiltonian. So just to repeat what I just said, but kind of slightly more mathematically. So you start with the initial state, n copies of rho. You apply the pulse. You let the Hamiltonian evolve the system. You invert the pulse, and then you measure. OK. So how do you actually use this? Well, if you were to do this multiple times, you could get some data and draw a plot. Here, this is the expected number of atoms in the E state after evolving for time t. And as I wrote down before, you could write this big, long equation of how to calculate it analytically if you knew rho. But you can actually, well, I should mention that So this initial state rho to the n here, we've evolved it by something which is a pulse applied symmetrically to all atoms on the EG levels, which has SN cross SUD symmetry. We evolved it by an SN cross SUD Hamiltonian, and then we inverted the pulse again. All of these things have SN cross SUD symmetry, so essentially we are applying some SN cross SUD symmetric operation to the state. So you can use representation theoretic techniques to recover this formula here. And essentially the same thing happens. In some sense, it's the same as measuring a particular Young diagram. But now we get around the problem of having degeneracy in our energy levels. Okay, so because we have a formula for this thing for different spectra, P, and we have data, then we can fit the data and infer the spectrum. Okay, so that's the end of my talk. But I should just summarize. So this is work which should be experimentally accessible, and actually one of the co-authors, Gretchen Campbell, is preparing to implement this. At the minute they're working on building the square trap. And in this particular system, there are things that it would be useful to learn the spectrum of the density matrix of nuclear spins in atoms for condensed matter purposes. So it should be useful independently of just an interesting quantum algorithm implemented in practice. And there are open questions too. I would say that kind of a burning one is, so we have this system with this high symmetry where we implement spectrum estimation. Can we do more general things with the same system? For example, implement the full Schur transform. Also, are there other natural systems for small quantum computing tasks, which are kind of maybe similar in spirit but different in practice? And also, even in the fault-tolerant full quantum computing setting, maybe we should be thinking a little bit along these lines of having parts of our computer which have special properties to implement particular algorithms, and other parts, I mean physically, they're kind of well-suited to fault-tolerantly implement, I don't know, some particular algorithm. Okay, that's it. Thank you.
Questions?
Could you tell us how this B beta removes the degeneracy you mentioned that exists? So you said many Europe's can have the same energy. How does this B beta remove that?
It's quite a difficult thing to describe, but essentially what it does is it creates a superposition of lots of different energy levels, essentially. So it somehow captures more of the, well, maybe another way to put it is the operator that I mentioned at the end that includes the evolution, the time evolution, and V beta and everything else. It's a much more general operator, a much more complicated looking operator, but which has, again, the irreps as its eigenspaces. And so there isn't the same constraint on that operator of having these degeneracies. I can describe a little bit more detail afterwards, but yeah, it's quite lucky, actually, I think. We weren't necessarily expecting that to happen, but it was.
So there's no representation theoretic reason why this. Well, we can talk about this later. I was just wondering if there's a simple way to explain.
It's a good question, and I would also like to think about it. So yeah, let's chat after. Thanks.
So back to your original definition for the small quantum computer.
Yeah.
So I can somehow see how in your setup you can get around the requirement of scalability and universality, but I somehow don't quite see how you can get around the requirement for error correction. Like, why don't you need error correction? So my problem is somehow this. You're proposing an experiment where you put n atoms in a trap and I'd intuitively assume that the best you can do in the lab is tune each of the atoms to an order 1 error. So in the Hamiltonian, you'll then end up with an order n error. Probably it's more like an order n squared because you have order n squared terms, right? But yeah, so basically anything you do will end up with an order n to an order n squared error, whereas you're trying to calculate the spectrum to order 1 error. So how can you do that without error correction?
I mean, in principle, I completely agree with you. I think that it's kind of if you're looking for something where you require really large numbers and you don't have any error correction, then you're going to run into problems. I guess the hope is that the errors are sufficiently low in the physical system so that you still do something useful. And it depends on the physical details and what kind of accuracy you're looking for, whether that will be the case or not. But I agree, I mean, this is not something, you can't scale it, I mean, by definition. It's a small, yeah. I'm sorry, I'm sure that is a completely unsatisfying answer to your question. Yeah.
So you described in detail what kind of Hamiltonian you want to implement in order to have the atoms evolve under this symmetric way, but how would you actually bring in the n copies of your density matrix rho into these atoms?
I think it's a very good question, and it depends completely on where they are beforehand. I mean, if they are, for whatever reason, if they're already in the atoms, for example, that's the simplest scenario. Maybe there's some experiment that you perform and you want to, the final nuclear spin state of the atoms, and maybe their entanglement to something else is what you want to learn about, then it's very direct, it's already there. If you want to transfer it from some other degrees of freedom, say electronic spins in some other atoms, then you can kind of concoct ways to do that, but it's obviously much more difficult. And yeah, it depends if they're in photons, maybe it's even more difficult. I mean, it depends where they are beforehand. Yeah.
I don't understand your obsession with the square. Well, why can't we just apply pulses that will swap them and use like average Hamiltonian theory to tell us that the average Hamiltonian is permutationally invariant?
That's a good suggestion. I think that's a clever idea. I mean, part of the thing that we like about this particular experimental implementation is that you actually don't need very much control at all. We didn't really do very much. All we did was prepared the state, which I guess is a bare minimum. We didn't care what spatial state they were in at all, so you can just throw the atoms in the box. Temperature doesn't really matter as long as they're in the box. So they can't be too hot to be outside, to kind of leave the box. And then you apply a pulse, which is the same to everything, so that's very experimentally accessible. If you want to get down to kind of individual control of particular atoms, then I think that's generally a much more difficult thing. But I think it's a good idea, and maybe in some other system that could maybe be applied to kind of create SN symmetry where you don't have it.
Thanks.
Let's thank the speaker again. Just to remind you, we have a short poster session. It's a 1 hour starting now.